Chapter 4, the electric potential field, a topographical parameter. The potential function is a game changer. In conceptual understanding as well as problem solving. It is the very best way to do physics. As an analogy, let's look at your calculus-based mechanics. In your mechanics course, whether you call it Physics 4A or Physics 7A, one starts learning physics using kinematics and Newton's laws. Unfortunately, this is probably the worst way to solve problems, as well as physical understanding, especially when it came to variable forces. Variable forces require solving differential equations. But then you cross the line. And maybe because it's red, we'll call it the parting of the Red Sea. The concepts of work and energy is a paradigm shift. In thinking. The usual way of doing mechanics is quickly replaced with conservation laws. And the three main conservation laws in mechanics are conservation of energy, conservation of momentum, and conservation of angular momentum, which is significantly better for problem solving but especially in conceptual understanding. So let's just do just a very brief review, really just 2 comments, not even a review. So I'm just gonna, this is going to be a very brief review of work and energy due to, let's just say, of work and energy. So the first thing that we should do is define what work is. The work done by a force can be written in one of 2 ways. So if I go from work from 1 to 2, then this is going to be the force dotted with the displacement. And this is only, so this is valid for constant fields. We only know of one constant field. That constant field is the electric field of an infinite plane. Compared to the work done from going from 1 to 2, where the force now is a variable force. Here, when I'm looking at this force here, this is for, so you have a variable force or fields. And in this case, we're talking about the point, the sphere, the cylinder, etc. So those forces play a different role in each of how we solve for it mathematically. The second point, which is the most important one, is 2. If a force is conservative, then the work done has these behaviors or properties. The first one is path independent. Path independent implies it only depends on the endpoint. That's a big shift. Like, for example, if you look at mechanical energy, so for example, for an isolated system, we know that we can define this thing called mechanical energy. And for an isolated system, this is a constant, which then tells us that the energies could be any number of energy states. But that really tells us that when I compare two energy states, that I actually don't care what happens between point one and point two. So that means that when I look at these, not only are they path independent, but it only depends on the endpoints. And then the other thing here, if I do have a conservative force doing the work, one can define a potential energy function. So from the work energy theorem, it just says that if I do work from 1 to 2, then I can define a potential function which is the negative of the potential between 1 and 2. Now, what is the potential function in terms of fields? One main characteristics is if I have an object moving with the field, there is a decrease in potential energy. On the other hand, if I have it moving against the field, then instead of a decrease, it's an increase of potential energy. Let's look at this as an example. Gravitational fields are conservative. And have a potential energy function. In other words, you can define a potential energy function. Throwing a ball in a G field can then have this effect. So if I'm, let's say, throwing it down, then if I define this as the ground here, and I have a gravitational field like this, it's always going to have a force of gravity pulling it down. So now if I copy this, because I'm going to need this 2 times, Here's what I'm going to find. That if I take this ball and I throw it and it's moving downwards, and if I have, and because my displacement is going downwards, I'm going to find that the ball moves with the gravitational field. The displacement and the force are in the same direction. That means it's positive work. But we know that the gravitational potential energy decreases as it moves downwards. In other words, positive work and the direction of the field then results in a gravitational decrease energy. Well, I can do the exact same thing if I'm throwing it throwing it up. So now in this situation, I have the ball starting at the bottom and it's going to move up towards the top. And this time the displacement is going upwards instead of downwards. We could then say the same thing. Ball moves against the field. And as a consequence, you see that the force and the displacement are opposite. So I am doing negative work, but it's rising in height. So its gravitational potential energy increases. So it's the opposite. So if I have gravity doing negative work, then the gravitational potential is positive. Once again, the main characteristic is if objects move with the field, there's a decrease. If objects are moving against the field, there's an increase in potential energy. So field-wise, that's the way we want to think about. We now apply this type of thinking to the work done by the electric field. Because electric fields are conservative, one can define the electrical potential energy function. And for abbreviation, you'll see me write electrical potential energy. So what I want to look at is that I want to do work with my hand for two situations. So I will do work with my hand for two situations. One, we're going to compress the spring. And two, we're going to push a positive test charge towards a charged sphere. And they represent, I mean, they're both identical in how you should think about it. So let's talk about compressing a spring. So what I imagine that I have a box or a mass, and it's going to be attached to a spring. And let's say that it's attached to this wall right here. And so what's going to happen here is that we're going to compress this. So that means then I'm going to take this block, and you're going to see here that I have now compressed the block. So what I imagine here is that I'm going to apply a force on this block right here. So this is going to be the force of my hand. Now, as I apply a force on here, the spring is going to react. And by Newton's third law, this force has to be equal and opposite to the spring. So if I say that this here is the spring force, by Newton's third law, that means that this has to be equal and opposite to my hand. So if I displace this, let's say this distance right here, what you're going to find here, as I start to push, I have to push harder and harder, and the spring force has now increased. So now I have a larger spring force, and of course the force of my hand has to be equal and opposite. Now we can look at this two different ways. We could look at this in the language of my hand, or we can look at this in the language of the spring force. So I'll start off with the force of my hand, but then I'm going to change it to the force of the work done by the spring. So the work done by my hand does positive work. And that's not a surprise, because the work by my hand adds work to the system, which increases the overall energy. It does positive work because the force of my hand and the direction of the displacement are exactly the same. So there's two ways to look at this thing here. So the two ways we can look at this here is that we could say that the work of my hand does positive work and increases the energy of the spring. So the spring potential increases. Or equally, I could then say that the work of the spring is equal to the negative of the potential of the spring. And this causes an increase in delta U spring. So the key point here that I'm showing here is this right here. This is the key point. is that the negative work of the spring caused an increase in spring potential energy. Now, what does this mean picture-wise? So picture-wise, it goes something like this. I prefer one picture over the other, but I typically draw the second picture because it's easier. So let's imagine that I have this scenario here. I have this amount of initial potential energy in the spring. Okay, so this right here is my initial spring energy. Now I'm going to do work. As I do work, I'm going to do this amount of work, and this is going to be the work done by my hand. Now remember, this thing is equal and opposite to the electric force, the work done by the electric force. Now this guy here, what ends up happening is that the work does not disappear. It does not disappear, but it reappears as energy. So what the work energy theorem is telling us is that we start like this. So what does the work actually do? It doesn't disappear, it reappears as the change in the spring potential energy. So this whole thing here is what we call the second energy state. Like I said here, I like this thing because it's physically correct. I mean, the other one is too, but this is super clear. We can see here is that here's what's the important thing. The work does not disappear. We say that the work does not disappear, but reappears as stored work. And that stored work is that what we define as the spring potential energy. And in this case, we're talking about this here. That's what that means. This is my preferred picture. I typically don't draw it because it's a lot more work. But this is another way that you could look at it. So if this is confusing, another way that you could think about it is that you have your spring potential energy. You now do this amount of work. And now this is the work of my hand. And so as a consequence, I now have a higher energy state in my spring potential too. So that's another picture. Like I said, I prefer the one on the left. So now let's do the exact same thing for a moving charge. So now I have a moving a charge. So I'm going to try to do the exact same thing. So this is very similar to spring analogy. So now what I imagine here is that I have a sphere that's charged. So here's my sphere, and this guy is charged. Now, when I say that it's charged, what we really mean here is that there's an electric field that's out here. So I'm going to pick, so what you're seeing here is that you're seeing this, is that there is a field, an electric field, and we've already talked about what that field looks like. So now I have a chart. So I'm bringing in a charge from here, and this is a positive charge. And as I bring it in, once again, I'm applying a force of my hand. And this has to be non-electrical work because the electric force will not be able to do that. But either way, I still have some electric force which is equal and opposite to the force of my hand. Again, this is going to be work done by, by a non-electrical work. But the fact is here is that it is still, work being done. And so as I get closer, the electric force grows in strength. Again, the reason why it grows in strength is because it's position dependent. So now I have now moved this guy from here to here. So then I play the same role that I did before. So then what do I see? I see that the work done by my hand does positive work. Since this guy has the force of my hand and the displacement are in the same direction. So then that really tells us then that there's two ways to view this, that the work of my hand, which is external to the system, does positive work and it increases the electrical potential energy. But that's not the way we look at it. We want to look at it in terms of the electric field. So then we could say here, then the work of the electric field is negative work because they point in the opposite directions. And as a consequence, I now increase this negative thing here. This is an increase in delta UE. This is what we're after. What is the electric field doing? Not what my hand is doing. So picture-wise, it's the exact same picture as we drew before. So to try to put this in the language, in terms of a picture, this is what I have. I have an initial electrical potential energy state. And it's always, it's going to look like this. So now what happens? There's the work of my hand. And the work of my hand, what it does here is that it transfers completely into the change in electrical potential energy. So if I look at this, what I'm seeing here is that there's a one-to-one correspondence between the work done and the change in potential energy. Again, this is my preferred picture. So when I look at this whole thing right here, this is the second potential energy state. Once again, work does not disappear, but reappears as stored work. And in this case, we mean that we've stored it in terms of gravitation, electrical potential energy. So then the question is, where does the potential energy get stored? Right? If it's stored, it's got to be somewhere. Well, you may have guessed it, it gets stored in the field. So let's talk about the spring and then let's go to the electrical one. So for the spring case, the stored work appears to be in the spring itself. And the reason why this is that there is a clear change. And I'm going to say deformation just because I don't have a better word at the moment of the spring. So let me show you what I mean by that. So if I have a block right here, and now I'm going to start pushing this. And if I continue to push this block, maybe I do this different distances here, and let's say that I do it like this. So let's say that this right here is where the spring is attached. So now if I start pushing on the spring, I'm going to say that right here, I have a relaxed spring. So if I have no compression, that implies I have a relaxed spring. And so therefore, no stored work. But now if I start to compress it, you can see that the spring is now compressed. So what do we say? We say this is low compression. So now what we're seeing here is that we now have a small amount of stored work. So then we say here is that this is low potential energy of the spring. However, if we come here and it's really compressed, then we're going to say that we have high compression, and as a consequence, there's a large amount of stored work because I had to push harder. And so therefore we say that we have high stored work, which tells me I have a high spring potential here. The same type of thing, the same thing occurs with electric fields. Stored work goes into the electric field. So when two interacting fields or two interacting when two fields interact, the E field lines are distorted. They get slash compressed. You'll see what I mean here. So if I look at this, what I'm going to do here is that I'm going to look at images. So what I did here is that I used this app called the Electro Static 3D applet. And what I did here is that when I did this here, I'm pushing a charge equal to 2e towards a source charge of q equals to 5e. And so this is what I see here. So there's two images that I want to show you. Here's the first one. And then the second one looks like this. So what you want to think about here is that look at the distortion or the comparison of the field. So over here, what you're seeing over here is that note that these have, uniformly spreading out field lines. But look where the field lines are changing. So if I look at this line right here, you could see that there's a small distortion. And then you'll see here that there's another distorted line here. So the range of distorted line is between here and here. So you're seeing that there are a few lines distorted by this charge of 2. I probably should have written this. This is the charge equal to 2e. This is the charge equal to 5e. Now remember, I don't care about the 2e charge. I'm only caring about the source. So because I have a few lines distorted, and they're not distorted very much, we then say that we have a lower electrical potential energy. Now let's go to this next one here. So remember, up here, just like I said up here, I should probably just copy this. Come on, that I copied this. Apparently not. So right here, this is the undistorted field. So, but now look where the field starts to get distorted, like here, and it looks like even all the way up to here. So what you're seeing here is that there is a lot more distortion here. So what you're seeing is that there are numerous lines distorted. Now, one of the things I want you to think about when I also say distorted, look how the field lines are being what? In this case, they're being compressed too. So as a consequence, I must now have a higher electrical potential energy. So I could say the same thing as I did up here about the amount of compression, whether I have low or high potential energy. And so I could then say here is that if I have a smaller distortion of field lines, then I'm going to have a lower amount of stored work, which we then call the potential energy. Or I can have a higher distortion of the field lines, which then gives me a larger amount of stored work. So, in summary, by looking at how much the E field lines get distorted, it tells us about the amount of electrical potential energy in the field.